So for example, for the spring here on page 1 of these notes here, this spring, the virtual displacements would be du, just a little wiggle here, moving to the right of the equilibrium position. Then this load F would do positive work. And the change in strain energy from the spring is K times D, which is the force, times du, times that tiny distance. It's not 1/2 K times D times du. Okay, so let's repeat this. If we have the force applied here and we're in the equilibrium position and then we do a small perturbation or a small wiggle, that force in the spring is already in place here. Okay, so it's K times D times du. There's no 1/2. The 1/2 is when we're slowly ramping things up here. So we have the external force du is equal to K times D times du. Those two are equated, and the change in virtual work we're going to call dV. So that is due to a little wiggle here. And we have our big red box formula, so put a box around this. dV, the change in virtual work, is equal to F minus KD times du. The hardest part for students, I think, is the signs. The one way of approaching this is to think, you know, kind of physically, that the minus sign means that the spring wants to go to the left, but the perturbation is to the right. So we have negative work here. And then for what we say admissible configuration. So what does that mean? Admissible means that you cannot violate compatibility. So you got to go back to chapter 2 and remember what is compatibility. And then you could also not violate essential support conditions, these essential boundary conditions. And we'll get into that soon in chapter 4 when we can violate some boundary conditions but not the essential ones. So we set the change in virtual work equal to 0 for admissible virtual displacements. And then we would have, for instance, 0 on the left-hand side of the red boxed equation is equal to F minus KD times du. The du cancels, so we have F is equal to KD, which is completely obvious. All right, so let's do an example on the next page.